and to all the organizers of this seminar series. I want to thank you for the opportunity to give this talk. I'd first like to talk a little bit about my collaborating scientists or co-authors on this, really. William Barney Balls from Bigelow Lab for Ocean Sciences, who I know has given talks in this seminar series earlier. George Aiken of the U.S. Geological Survey, Boulder, Colorado, who very sadly recently died. Mike Billmeyer, Michigan Tech Research Institute, Justin Sheffield, Princeton University, Lifeng Liu of Michigan State University, and Colin Russler and Phil Camille of Bowdoin College all made significant contributions to what I'm going to be presenting. Okay, sorry, ahead of myself here. I'd also like to acknowledge laboratory analysis by Kenneth Butler at the USGS in Boulder, Colorado, and Anna Burakovsky at Bowdoin College. And in addition, many people from Bowdoin who helped do some sampling for this study. And then all the hydrologic technicians with USGS who've been making discharge measurements since the early 1900s that make these time series analyses possible. So just an outline of the talk. I first want to talk about long-term trends in climate and hydrologic variables, then go over the low-test regression model that we use to estimate DOC fluxes from rivers, then a little bit on the factors that influence DOC concentrations and fluxes, then some historical trends in DOC flux, and future projections for trends in runoff and associated DOC flux. And then finally, some implications of ongoing trends, some implications of these ongoing trends for ocean acidification. And here I'm starting to get beyond my level or my area of expertise, so just a warning on that. So setting the stage spatially, these are the primary rivers I'm going to be talking about and their drainage areas that flow into the Gulf of Maine. And further setting the stage, I just pulled this down from a NOAA website very recently, showing the time series for temperature on the upper panel from 1895 to 2016, showing about more than 1 degree C rise in temperature over that period. And then the trend for precipitation, which is also increasing but much more variable and smaller in terms of percentage increase overall. So the first study I want to talk about is where we looked at how ongoing climate change is affecting runoff to the Gulf of Maine. And in this study, we looked at trends in precipitation, runoff, and evapotranspiration for 22 rivers that have at least 70 years of runoff data through 2011 in this study. And the basins are shown in these various hatches and stipples here that have this long-term data. So precipitation increased in all basins, was significantly, the trends were significant in 19 out of 22 basins. Runoff increased in all basins as well, but was significant only in about half the basins. And evapotranspiration increased in 16 of 22 basins, but very few were actually significant changes on the ET side. So just want to draw your attention to these rates of increase in runoff that I've shown here in with this red box, ranging anywhere from about 10 to more than 30% increase. And these are for the periods of record, which varied anywhere from about 103 years up to 70, and with an average record length of 87 years. By the way, the precipitation data that we used was the PRISM, this Parameter Elevation Regressions on Independent Slopes model out of Oregon State, and that data set is dating back to 1895 is what we were able to use, the monthly precip numbers. Okay, so in addition to the annual increases in runoff, what I'm showing here is the average area-weighted averages in terms of monthly changes. This on the panel on the upper right shows the monthly trends in terms of cubic feet per second. And what you see here is that we're seeing increases in most months. They're significant in fall and winter months. Trends are not significant during the summer months. But what you'll notice here is that we see decreases in May and increases in March and April, and that's what we're going to show in a minute is really a result of earlier snow melt and earlier runoff. The other one of the interesting features of changes in runoff over time is an increase in the variance in mean decadal runoff for major rivers in the Gulf of Maine watershed. This is the data for the St. John, the Saco, the Kennebec, and the Androscoggin for the largest rivers. And we're showing standard deviation of the decadal mean runoff. So we took 10 years to calculate the standard deviation and then just plot that through time. And what you see is a rather striking increase in variance over time. Now, Barney, I think, in his talk showed increase in variance and precipitation, which of course is driving this. And along with increases just in total amounts of precipitation, we're seeing, or has been published, increasing frequencies of extreme events. This is important because what this means is that on a more frequent basis, we're getting large export of fresh water and nutrients and organic carbon coming off these watersheds. Turns out that the northeastern United States has some of the highest increase in the frequency of extreme events. And now, in this particular study, extreme event is defined as the 1-year recurrence interval storm, which I believe in Maine is somewhere in the range of 3 inches or so. So we're seeing increases in that. And I've got a couple of slides that show this effect. This is the Deerfield River at Shelburne Falls, August 28th, Hurricane Irene. Some pretty dramatic photographs that show what was measured as a peak flow near Deerfield, Mass. of 89,000 cubic feet per second, which is estimated at around 200-year recurrence interval storm. So not to be outdone, in southern Maine, we've had a lot of extreme event or extreme weather in recent times. This particular study highlighting here is showing that for this April 2007 storm, a series of sites were estimated to have their storms of recurrence interval between 50 to 100 to greater than 500-year recurrence intervals. But what was particularly striking was that this April 2007 storm followed a flooding in 2006 in southern Maine, where some of these rivers experienced 50 to 100-year recurrence interval flows. So people were beginning to wonder whether or not we knew how to calculate recurrence intervals at this point. So I just want to frame this in the context of intensification of the hydrologic cycle, because this is how I see what is going on with hydrologic changes in response to warming. And namely, showing this hydrologic cycle here, warmer conditions mean more evaporation off land and the ocean, increasing atmospheric water vapor content, increasing precip, and in some places increasing runoff, depending upon whether ET over land is greater than the amount of increasing precipitation. And so the way I like to think about it is in terms of how does this influence the probability or likelihood of extreme events occurring. I think Kevin Trenberth has probably said it best, that you can think of this as a warming-induced increase in atmospheric water vapor content that essentially loads the dice for heavy precipitation events to occur. Now, this doesn't mean that every big storm we can say was caused by climate change. It just means that the probability of these bigger storms is likely increasing because there's more water vapor in the atmosphere. Okay, so another study that I was involved with was Catherine Hayhoe et al., in which we looked at the Northeast United States and used a series of different emission scenarios and global climate models, and then on top of that laid the variable infiltration capacity hydrologic model that Justin Sheffield and Lifeng Liu worked on to generate projected trends in runoff. And one of the things we did was looked at potential changes in stream flow quantiles. What are shown here is for the area-weighted discharges, cubic meters per second per square kilometer, for these various quantiles, 5th through the 95th quantile. And what I find interesting here is that sort of counterintuitively, we're expecting both flows at the higher level to be increasing, these 90th, 95th flow quantiles, so increasing flow at high flow, but also decreasing flow in low flow. And this sort of all coming together, thinking about longer summer dry periods, warmer summers in which evapotranspiration is essentially winning out over any increase in precip, and you're likely then to see lower flows in summertime. And another part of that study was looking at how some of these changes in runoff might influence the period of summer low flow. So what's shown here is 51 stream 30-year area-weighted average flows, comparing the historical observations 1961 to 1990 in this black trace with the what would happen if we had the high emissions, the Hadley model, high emission scenario, the A1, versus a low emission scenario, the B1. And what's evident is that we're seeing both an expansion of this low flow system, as you can see by comparing the red to these other lines, so the high emission scenario, and also a decline or to summer base low conditions earlier in the year, and particularly later in the year. Both of the low emission and high emission areas show that you return to sort of more normal flows later in the year. And another aspect of that study was looking at the probability of changes in drought conditions. And I'm showing just one little piece here, which on the left axis, these plots refer to the number of short-term droughts of duration 1 to 3 months that might occur in a 30-year period. This top panel is 1961 to 90 historical period, where you're looking at maybe somewhere between 5 years out of 30 up to maybe 15 or so, and then a low emission scenario, and then the higher emission scenario. We see that we're expecting that kind of a drought to occur nearly every year or every year. So you probably know that we've had a pretty severe drought in 2016 that continues in terms of groundwater levels up until today. And what the climate models are suggesting is that it's likely that these are going to continue. This was the U.S. Drought Monitor report for October 18th, showing extreme drought throughout parts of coastal Maine, New Hampshire, and Mass, and various drought conditions throughout the rest of the region at that time. Now, as to the question of whether or not it's actually we have a trend in droughtiness. This is the Palmer Drought Severity Index plotted versus time for NOAA Climate Division for central Massachusetts, and you see that there is a slight increase in droughtiness over time. So we also know that, as I said before, that warming is changing the timing of snowmelt and the associated spring freshet across New England. This plot shows the locally weighted scatterplot smooths for winter, spring center of volume dates for the 13 longest record rivers in New England. And what the center of volume is to us is if you picture the amount of water that's going to flow by a gauge between January 1st and June 30th, it's when half of that water has come by the gauge. And what we're seeing is that about a 1 to 2 week advance in that timing as snowmelt's occurring earlier. So, and it varies, of course. The more northern Maine sites appear to have slightly lower rate of change, and the central Maine and New Hampshire and Vermont have the greatest rate of change compared to more southerly sites in Connecticut. This same phenomenon of earlier runoff has been shown in my colleagues Glenn Hodgkins and Rob Dudley at the USGS have shown this across the northern tier states. So you can see throughout New England occurring again about 1 to 2 weeks earlier, and occurring earlier pretty much throughout the region. So it's a very general phenomenon. Now, one of the things that's driving this is changes in the ratio of snow to total precipitation. So I think of this as we're getting more rain in winter, more rain on snow events, which is both getting the snow to a higher density so it will melt earlier and run off earlier, but also getting more winter runoff. And this study on the right that I did covering the dates 1949 to 2000, and these downward-facing arrows are sites that are showing significant reduction in this ratio of snow to total rain or total precipitation. You notice there's some sites here in the New Hampshire, Vermont that are not showing any changes, and this later study sort of reinforces that, again, being a phenomenon occurring across northern tier states. And I blew up New England to show that, again, we're seeing, they saw a little bit, extending the data through 2005, the same sort of phenomenon of decreasing ratio, which is, I think, is driving this earlier snow melt. So shifting gears now to look at the low-density regression modeling, which is what we use to estimate dissolved organic carbon fluxes. This model is calibrated using discrete pairs of dissolved organic carbon concentration in samples collected and the instantaneous discharge at the time that that sample was collected, as described by Runkle. LODES determines the best regression model based on this CACI information criteria. And it's important to note that for this analysis, we use the best model that explicitly maintains the same seasonally dependent concentration discharge relation over the entire estimation period, which permits us to allow these longer-term extrapolations, which LODES was not originally designed for. But by restricting it to the same seasonally dependent concentration discharge relation, you don't let it drift over time as it would if you allowed for it to pick a time term. This regression model then implements sine and cosine terms to reflect the seasonality, kind of a sinusoidal effect. And dissolved organic carbon, it turns out, is particularly appropriate for this because we do see such variation between seasons in concentration and in the concentration discharge relation itself. The model has some limitations, and one of the significant ones is that it can't really simulate hysteresis. So it relies on you having sampled enough on the ascending limb and descending limb to sort of balance the effects of hysteresis out. Perhaps more importantly, the model is subject to seasonal bias due to the model's fixed shape of this relation, which in reality may differ. But this could be tested for, and we found some seasonal bias, a small bias in wintertime, positive bias, but little bias in other seasons. This equation basically shows the kind of format you get, the coefficients that are assigned and the sine and cosine terms that define the shape of the concentration discharge relation. So what do we do with this? Well, one of the things it does is it helps us understand the major factors that are controlling DOC flux. We did a study published in 2013 where we looked at a number of basins, sub-basins within the Penobscot River drainage, and looked at, for a 4-year period, sampled these things so we could develop what I refer to as a response surface for each of these. And the response surface is how DOC flux is going to change, shown on this axis here, with increasing discharge on this axis, the month of the year here, and then draped over that, I've shown the DOC concentration. So what really strikes you from looking at this plot is that in response to discharge, the DOC concentration is much more sensitive in summer, fall, and early winter than it is in late spring and winter. So you get almost a doubling of concentration with increasing discharge in the summer, but very little increase in the winter time. So we also noted that the relative contribution to the total DOC flux from each tributary varied by quite a bit by season. For example, this west branch of the Penobscot yields substantially less carbon in the summer compared to the other river basins, but more in winter, and we believe that's because these reservoirs dampen the normal variation in DOC concentration in the system. And I'm going to get to the importance of wetlands are really one of the factors that are most important in terms of explaining the differences between tributaries. The pictures on the bottom show the Suncaze Meadows National Wildlife Refuge, which is really a rather large complex of peatlands, the largest in Maine anyway. And showing in these figures are how DOC concentration in the various tributaries that we sampled, or Bowdoin College people sampled from the St. John, Penobscot, Kennebec, and Androscoggin, showing a nice relationship of increasing concentration with wetland area. And you see the same thing if you look at carbon yield per unit of runoff that I'm showing here in the right-hand panel. So wetlands are, as many other people have shown, are really important to regulating the amount of carbon flux. Another thing we can do with this regression modeling, and I'm showing that here, is looking at 4 different years. This is based on the hydrograph, but also based on what the regression model is telling us for a given discharge you would get for DOC export. And so draped over that is the DOC concentration. And this is going to come up a little later in the talk, at the point that 2004 was a particularly dry year, as you can see by the amount of DOC flux, whereas 2005 was an extraordinarily wet year, and particularly had major storms in the fall when we have the highest concentrations of DOC. So, okay. So now on terms of the trends of DOC inputs to the Gulf of Maine over time, we looked at these series of major watersheds between 1930 and 2013, showing that in these are the increases for these major rivers: Merrimack, Saco, Androscoggin, Penobscot, and St. John. And all of these, except for the St. John, were significantly increasing trends. And I'm going to just show you this is another way of looking at that. The major rivers, this is annual DOC export over that period, ranging from a low of 13 in the St. John to a high of 47 for the Merrimack. Again, driven largely by the change in discharge, of course. And this is in the winter, which is even larger increases. But here the increases are larger in the more northerly watersheds, where in times past these things were much lower flows in winter. But as winter flows have increased, and these higher latitudes, we're seeing much more DOC export. And again, ranging from around 200 to 40% from north to south. And so this looks very familiar to our trends in monthly runoff. These are trends in monthly DOC export. Again, for the same reason that we're seeing increasing runoff, we're seeing increasing DOC export. And again, it looks like by decreases in May and increases in April and March, we're seeing that shift towards earlier runoff. All right, now I'm going to shift the gears entirely and look at one sort of potential consequence of increasing DOC export to the Gulf of Maine. This is work that Barney Balch at Bigelow Lab led, and he has reported on this earlier study in one of the earlier NECAN webinars. But for people who hadn't seen that, I want to emphasize the role of DOC and increasing freshwater export as a part of that. So what you see in this panel here is that DOC export from the 10 largest rivers to the Gulf of Maine between 98 and 2010, increasing over time as a consequence of discharge. And then what Barney has shown is that where you have higher CDOM measurements as measured by this absorption at 412, you see an association between that and increasing discharge, and that's what's shown in this plot. So where we have higher discharge, we have higher CDOM. Okay, and so this is I should mention the transect that we're going to be talking about from Portland, Maine to Yarmouth, and you can see where the Penobscot River mouth of the river is there. So in that same study, what was particularly interesting to Barney was in his along this transect, which has been maintained since the late 1990s, he shows here this Hofmüller plot that looks at latitude is running along what we think of as the y-axis here, and time along the x-axis, starting in 2002, running through 2010 in this study. And what was interesting was that we appear to see a substantial decrease in photosynthesis across the whole Gulf here in that study. And this by the way, is Barney working inside this lab, portable lab, which in this case is being loaded onto the Argo, a ship that I unfortunately decided to volunteer for a field trip on, and got, I was so sick on the ship for a day and a half or 2 days that I couldn't do anything, but I tried. Okay, so Barney et al. In 2016 published this follow-up study in which we looked at the same kinds of variables, but what I'm going to now do is focus on what we kind of learned more about how runoff was interacting with what he's seeing in this transect, and more generally for satellite-derived measures of CDOM. So what's shown here on the left panel is the lag correlation coefficient between monthly average CDOM absorption derived from Modus Aqua AG412 at Syracuse Buoy F, which is located right there at the mouth of the Penobscot River, and it's the correlation between what CDOM is measured here and discharge from the 5 large rivers, so the St. John, which is coming out of the Bay of Fundy, the St. Croix, the Denny's, the Narraguegas, and the Penobscot. So all this fresh water is going to be influencing this buoy, and we see a pretty good correlation between, with a lag of 1 month, between what you see for CDOM and what's coming out of these rivers. And in this study, continued the trend to looking at photosynthesis over time. The other study ending in 2010, there were a couple of years where it seemed photosynthesis rebounded, but it's come back down again. So the trend does appear to be continuing in terms of photosynthesis in the Gulf. So starting to tie this all together, the key findings were that the riverine DOC export to the Gulf of Maine was positively related to the satellite-derived shipboard measurements of chromophoric dissolved organic matter, CDOM, June through September, and through this period 98 through 2013, which is shown in this figure on the left. So this positive relationship between those. And another interesting aspect to this study was that Barney was able to calculate the 4LU color from the chromaticity that was measured in the current study, and finding that it varied between 4 and 18, or on average somewhere in this 10 to 12 range. And then he compared that to what Henry Bigelow measured 100 years earlier, which was in this 4 to 9 range, or saying like 6 to 7. So the idea is that the color has changed that much over time. So summarizing this, it suggests that increases in DOC export, the sea surface CDOM concentrations, and yellowing, increases in all these could impact transparency in blue labelings, and thereby be one possible explanation for the decrease in phytoplankton photosynthesis and productivity as previously postulated. So now briefly, some implications of increasing freshwater runoff and DOC export apart from these sort of changes in phytoplankton. And I just borrowed this from this is where we're going with this, that increasing inputs of poorly buffered freshwater to the Gulf of Maine containing nutrients that can promote algal growth, decay, and decomposition cause more acidification. So first I wanted to start with this quotation from the Bauer study. I mean, I'm sure that some of this is going to be very old hat to some of the viewers here, but I just thought that it was worth putting the work I'm talking about in this context, and for people who aren't aware of these studies. But it says that the elevated levels of organic carbon respiration in productive nutrient-rich estuarine waters and river plumes have recently been found to amplify the effects of ocean acidification on estuarine ecosystems, citing two people who I know have given talks for this webinar series before. So, and what I just show here is this chlorophyll concentration between 97 and 2010 climatology for the month of January, showing the higher levels of chlorophyll, hugging this coastal region that these rivers are impacting. And I understand, though, that of course the source of some of this increased algal growth and chlorophyll is thought to be, in fact, much of it may be Labrador current water that's crossing over the Scotian Shelf and forms up with the eastern Maine coastal current and the western Maine coastal current. So, and then as well as the upwelling of the nutrients that are brought in by that current are a major part of why we see the increased chlorophyll there. So this, I thought this was interesting to bring up. This is a slide from this paper in Nature Geoscience by Kai et al. And it's a conceptual model showing river inputs of organic matter resulting in acidification. I mean, that's the part of it I wanted to focus on. So he shows organic matter coming in here from the river and basically shown as if it were particulate organic matter settling out, decomposing, being respired, and then the resulting acidification effects. But I guess my question is, where is the terrestrially derived dissolved organic carbon? We know from work that Colin has done and other people in the northeastern rivers that in general we think of that the ratio of dissolved organic carbon to particulate is about 9 to 1. So raises the question to me is, what is the fate of this DOC? Is it decomposed in estuaries in the near shore in the water column? And I talked to Barney about this very recently, and he reminded me that George Aiken has shown with it that we have about 10 milligrams per liter on average when we're in the river before it meets the saltwater interface. But at the mouth of the estuary, it's reached 1 milligram per liter. So is this dilution, or to what extent is it rapid respiration within the estuary itself? We really don't know. Or could it be flocculating when it meets the salt water, some of it, and settling out, and then becoming later decomposed in benthic sediments per this sort of mechanism that Kai has suggested? However, Barney also pointed out that 1 milligram per liter seems to be conserved out of the Gulf of Maine into the Northwest Atlantic, or transported offshore and maybe to later be decomposed in the open ocean. So I think this is an important question that needs to be looked at more thoroughly, where the DOC is going and where it's actually, if it's impacting acidification, where is that occurring? So this from Donnie et al. This just stresses the fact that it's not just the organic carbon in this river inputs, but it's the nutrients that are coming in from rivers that can also help cause coastal eutrophication and hypoxia, and the acidification associated with that. Now, I was wondering whether or not people had actually identified the Gulf of Maine as an area where there have been episodes of hypoxia, and apparently that is true. There have been in the past, particularly in the Wells River and Casco Bay areas. Okay, so I think Rue mentioned this study, Gledhill et al. 2015, and I found it, it's very interesting if you look at the long-term trend in river discharge. This is what's showing here on the left is the annual average daily discharge for most of the large rivers draining, so summing them to the Gulf of Maine by calendar year. And these are the rivers shown here. So these are all the major rivers at their head of tide. And you notice that, first of all, there's an increasing trend, but 2004 was, as we said, a really dry year, and 2005 is the wettest year of record so far. So a huge variation there. And what this plot on the right is showing in this paper is that the difference in aragonite saturation for this dry year 20 2004 versus the wet year 2005. So in 2005, we have a lot lower aragonite saturation in these areas that are immediately down gradient from, so the Kennebec, but really it's the Kennebec plus Androscoggin that meet in Merrymeeting Bay and form a large river plume in that area. So notably, because freshwater discharge is expected to increase in coming decades, I think we should expect that we see these episodic depressions in aragonite saturation to occur more routinely. And I think this is maybe the final slide. And what this is showing is that I mentioned before, the Labrador Current, of course, crossing the Scotian Shelf and coming into the Gulf of Maine, is supplying these poorly buffered waters to the Bay of Fundy and the Maine Coastal Current. But that's also being combined with river discharge, particularly Penobscot and the Kennebec plus Androscoggin River system, and can result in what Gledhill describes as surface waters that can be corrosive, or aragonite saturations less than 1. And this shows, I'm showing here where the Penobscot is coming in, and the Kennebec, and the color scale showing that in this particular case, this is monthly mean minimums for aragonite saturation mapped over this area, and you can see that those areas in particular show low aragonite saturation. So if we compound that with large storm events that bring off a lot more fresh water and nutrients and carbon, we might expect an amplification of that problem of declining aragonite saturation. So thank you, and if there are questions, I'll try to address them.
Thank you very much, Tom. That was a great presentation. At the moment, I'm not seeing any questions from anybody typed into the box, but maybe, oh, we've got one now. We've got, that was great. So I haven't had a chance to read through this, so I will. This is from Joseph Kunkel. The Kennebec River, Popham Beach, used to, up to 10 years ago, have huge numbers of water-saturated wood pebbles in the surf that represented undissolved solids, presumably from the now terminated logging runs. Have those macro undissolved solids decreased as a product of the rivers, and is anything known about where these solids went, opposed to small particular undissolved solids? And is there any estimate of the dissolved versus macro undissolved matter carried by the rivers and deposited into the Gulf of Maine deep water?
That is a great question, but one that I know very little about. I do know that the various logging and mill practices have changed dramatically over the years, with many mills being shut down, and I suspect that a lot of that wood macro carbon wastes are still stored behind existing dams, and as some of these dams are breached purposefully, we expect that there will be more transported downriver, as was presumably happened when the VZ Dam was taken out on the Penobscot, although unfortunately we never had the kind of funding necessary to study that issue. But as to where it goes, this macro organic matter that you're talking about, particularly from the milling industry and paper making industries, I really don't know. It's a very good question, and probably many of the large river estuaries in Maine have, I'm going to guess, have a lot of that kind of legacy carbon in them. But whether it's actively decomposing or is being, transported out past the shelf, I really don't know.
Thank you, Tom. We've got a few more questions here as well. One from Dwight Gledhill. Why is New England exhibiting such an increase in high-intensity events relative to other regions of the U.S.? What unique attribute of New England makes it so much more sensitive?
I wish I could answer that question. I really don't know. Maybe I haven't done my homework on that well enough, but yeah, I guess I just don't know whether or not we're just in a location where atmospheric circulation that's changed over time, whether it's the North Atlantic Oscillation or any other of the teleconnections. We seem to be at a place where it's more sensitive, but why that is, I just don't know. But a number of lines of evidence do suggest that is the case, particularly these reports of increasing frequency of extreme events.
Thank you. Another question from Beth Turner. Is there any way to extend this to an economic impact? I'm thinking about the impact on ski areas and forestry with respect to the change in timing and type of precipitation.
I would imagine definitely so, especially with the ski industry, because I think, as you know, there's a lot of uncertainty in these models for sure, and particularly more so with precipitation than with temperature, and even maybe, you know, amplified when you're trying to talk about the future in terms of the ratio of snow to total precipitation. But that said, I would think that you know, ski operators would be very interested in people's best guesses in terms of how total amount of snowfall and timing of snowfall is likely to change in the coming years. I mean, I do know that southern New England has already experienced a situation where basically these ski areas, the smaller ones, are not, in the southern areas, are just not tenable without you know, substantial snowmaking. And we've had years where even in the higher elevations in more northerly ski systems, that they also haven't been, they would not be able to survive without snowmaking. So I would think that an economic analysis of that, it may well have already been done. I know there have been some papers on changes in snowmaking and I mean in ski area, skiable days and all that sort of thing. In terms of forestry, I'm not sure you know, how the changes in climate that we're seeing are likely to affect, in terms of forest productivity. I think that the modeling that's been done has suggested that the trends towards warmer and wetter conditions, if anything, are likely to increase the productivity of forests in New England, provided that we don't have these extensive droughts, or that we don't bring in more, you know, invasive insect pests. But in general, the climate would be conducive to more productive systems. If the other thing is that, you know, over the long term, we're likely to change the forest composition away from, in terms of spruce fir types, towards more of the hardwood and pine types.
Thank you. Another question from Chris Hunt. The St. John River water is relatively well buffered compared to the Kennebec, Androscoggin, and Penobscot. Do you think increased St. John discharge can offset some of the ocean acidification consequences presented by increased Labrador seawater and increased Androscoggin, Kennebec, Penobscot flow?
Yes, that would make a lot of sense to me. I really not been aware of the specific chemistry of the water from the St. John. Where we have actually sampled it and been able to get our long-term data from is near Fort Kent, right at the border with Canada. And I know there's a lot of land area that's in, some of which is in agriculture on the Canadian portion of the downstream St. John. And so it wouldn't surprise me at all if that's very true, that mitigates some of this effect of lower buffered capacity waters coming in from the rivers and from the other rivers in the Scotian Shelf. That's a really good point.
Thank you. Another question from Matt Liebman. You mentioned that there will be episodic decreases in saturation. Can you also address the timing of DOC exports to the Gulf of Maine? For example, export is earlier, so how does this affect production in the Gulf of Maine? Well, okay, so the export is occurring earlier, so
in terms of contributing to spring blooms, I would think that it will magnify the effects of the early spring blooms that are already observed as these the delivery of freshwater and nutrients becomes earlier in the year. But I'm not exactly, I mean, I don't know myself the timing of these early spring blooms, but I'm presuming that they're occurring at a time when increasing freshwater inputs will only serve to amplify them. But I'm not familiar enough with the timing of the the offshore blooms to be able to answer that very authoritatively.
Okay. And another question from Matthew Moretti. How and when do you expect these changes will affect the shellfish industry in the Gulf of Maine?
Boy. Well, I think there's a gradual cumulative effect of more episodic decreases or depression of aragonite saturation owing to this acidification effect. It's sort of a gradual cumulative thing, so you have more and more severe depressions are likely to have a gradual negative effect on the shellfish industry. Beyond that, I really don't know the timing of when it would become, sort of economically less viable to be, working in shellfish in this region.
Thank
leave
you.
That up to, no, go ahead.
Thank you. You were going to say you're going to leave that up to other people? Yeah,
people like Rick Wally for lobster and a lot of other people for different shellfish.
Okay. A question from Larry Mayer. A paper 33 years ago showed that summertime CDOM export from some estuaries of the Gulf of Maine can be dominated by materials from coastal macroalgae rather than rivers. Have changes in this export term been considered in these analyses?
In our analyses, we have not considered changes in export from those regions, specifically anything downstream from the downstream-most gauges on the major rivers, which are at the head of tide, more or less. So you're right. I think we should expect that along with changes coming out of rivers, we should expect changes in the estuarine environment where any of these factors that are likely to increase the decomposition of organic matter in them will in itself be contributing, or increases in just in the algal production in those estuaries. So that's a good point, but it's not been considered in this study.
Great. At the moment, I think we've got one more question, or it's more like a comment from Meredith White, who says, we don't see larger blooms in the Damariscotta River, perhaps because the increased CDOM may be absorbing the light and reducing productivity. So,
interesting. Yeah.
And I think that is it for the time being. So thank you very much, Tom, for giving us our presentation today and answering some questions. Oh, there's one last late breaking question from Bob. Is there a long-term data set describing the pH of the precipitation? Is acid rain playing a role?
There are definitely long-term data sets from the National Acid Deposition Assessment Program for the few sites in Maine where it's actually been monitored over the long term now, since I guess about the mid to late 80s. Basically the pH of the rain is low and has been low for a long time. There have been some relief from the taking sulfur dioxide out of, or some of the sulfur dioxide out of smokestacks. So the acidity of the rainfall has actually improved over the last 20-30 years, but it's still well below a level that it was pre-industrially, and so I'm sure it's having some effect on the chemistry of river outputs. I know that from a soils perspective, the the buffering capacity or the exchange capacity in soils has declined over time, and that's certainly influencing the pH of water draining out of soils and into rivers. So I'm sure it is a factor.
Great. Well, thank you again, Tom, and thank you everybody who's on the webinar for attending today, and we'll let you know when the next one is scheduled. So goodbye from all of us.
Thank you.